All right, so before we start lesson 6.1 part B, the law of Sines Ambiguous Case, let's think about all the ways that you remember from geometry that prove triangles congruent. So go ahead and take a moment to list all the ways that prove triangles congruent. So these are the 5 ways that you should have for proving triangles congruent. And 4 of the 5 apply to all triangles. The one that doesn't apply to all triangles is HL. HL applies to right triangles only. Okay. So the ones that apply to all triangles, they use sides and angles and different combinations of sides and angles. So looking at this list, if we think about all the different combinations of sides and angles that we could make that are not included in this list, those are ways that won't prove triangles congruent. So ways to not prove triangles congruent with combinations of S's and A's. So think about the combinations of S's and A's that we don't have in this list, and let's write them down for ways to not prove triangles congruent. So the 2 different ways that do not prove triangles congruent with combinations of S's and A's are SSA and AAA. Okay? And I always like to tell my geometry students that SSA, if you look at it backwards, is a bad word. It's a bad word backwards. So if it spells a bad word, you could also write it as ASS. It's the same thing. Those are the same thing. Because you can reverse it and it's the same situation. So SSA or AAS, a bad word or a bad word backwards doesn't work. And then just remember that AAA also doesn't work. Okay? So those ones don't work. So this is what leads into this law of sines, the ambiguous case. Okay? So the law of sines, we know the formula from yesterday. So we have the sine of an angle divided by its opposite side. So the letters have to match. Sine of A divided by A equals the sine of another angle divided by its opposite side. So those letters have to match, right? So if we think about what situations we're allowed to use this law of sines, let's just draw a little diagram here. So if I just do an A, a B, and a C, and then this is little a, this is little b, and then this is little c. So if I'm given a situation where I have this angle, and I have this angle, so I have 2 angles, and let's say I have this side, side C. This situation is something that I could use law of sines for. And you might look at that and you go, but we don't have one pair of letters that we know. However, I do have 2 of the 3 angles. So since I have 2 of the 3 angles, I could find the 3rd angle by using the triangle sum theorem. And now I have a pair. So I have sine of C over C, and then I have angle A. And so I could do sine of A over side A to find missing A. And then I could do the same thing with sine of angle B because I know angle B, and then find side C. So this situation here is ASA. So the law of sines would work if I'm given ASA. So let's think about the other situations when law of sines will work. So I want you guys to just pause and take a moment to think about the other situations of when law of sines will work. All right, one of the other ones is AAS. So if I just highlight on my diagram, angle, angle, side. That would work because I have a pair of matching A's. Okay? Or it could be angle A, angle C, and side C, which would also be fine because I have a pair of matching C's. Another one that we have is ASS. So in this case here, I have an angle, and then I have a side, and I have another side. So that works because I have the pair of A's, and then I could find the B, and then I could use my triangle sum to find the C, and then the missing side C. Or if I have ASS another direction, go A, and then S, and then S, that works as well, because again, I have my pair of A's. So ASS also works. All right, now when you look at these 3 options that we have, these are the only 3 options for using law of sines with given information of angles and sides. When you look at these 3, you're going to notice that 2 of them come from congruent triangles, and 1 of them does not. So ASA, AAS, here I have ASA, here I have AAS. So since those come from congruent triangles, that means no matter what I'm given, if I'm given a specific angle, side, and an angle, there's only one triangle that can be formed from that angle, side, angle. Because I know that that's a congruent triangle method, then I know that if I have that specific angle, side, and angle, that's the only triangle I can make. Okay? But then we have this ASS case. ASS case is not a way to prove that triangles are congruent. And so we can see that, okay, well, this ASS, well, that's over here. So what that tells me is if I'm given a specific angle and a side and a side in that order, then I don't know if a triangle that maybe I make and a triangle that you make with a given angle and two given sides is going to be the same triangle. I don't know. Because it tells me that I can't prove that triangles are congruent that way. So could there be two different triangles that I could make with that angle and those two given sides? And that is what brings us into the ambiguous case. So this ASS is called the ambiguous case for the law of sines. Okay. So we're going to investigate this ambiguous case, and we're going to start off with this chart here. And in this chart here, we're going to use this YouTube link that you see at the top of the screen right now, and we're going to follow along with a little video. And with this video, you're going to complete this chart. Okay? And there are going to be three different cases that we're going to investigate here that give us three different options of numbers of triangles. All right? Sometimes there will be triangle A number of triangles, or B number of triangles, or C number of triangles. And we'll see that just momentarily in the video. But I do want to preface that these three cases right here are starting off with the given angle here. Here's my given angle is 50 degrees. My given angle is 50 degrees. My given angle is 50 degrees. The given angle is always an acute angle. So for this situation, the given angle is always an acute angle. If the given angle is an obtuse angle, it's a little bit different. And we'll talk about that after these ones. So these three cases are for given an acute angle. So before we start this next little video within this video, you might want to pause for a moment and just take a minute to draw each diagram with the given information. So draw a triangle ABC for each set and label angle B, angle side B, and side C. So for example, for the first one, and I'm going to encourage you guys to draw the angle on the left. So angle B would be here. This would be 50 degrees. And then side B is obviously opposite that. So here's a 3. And then side C, I'm always going to put on the left side. So that means that this would be angle C and the top would be angle A. So take a moment to pause the video and get the other two diagrams drawn so that when you're listening to the next part, you can keep up and write down what you need to write down.
The side-side angle case, and why is the ambiguous case, and how 0, 1, or 2 triangles can be created when you have two sides and an angle. I'm going to do that by solving three different triangles and trying to demonstrate the three different cases that could happen. First, in this case, we're given the information in red that 50 degrees is the angle, 4 and 3 are the sides. And I'm going to try to show you why this triangle doesn't exist. First, let's determine the height. The height of this triangle is equal to 4 times the sine of 50 degrees, which is approximately 3.06.
So that height is just found by using SOHCAHTOA.
As you can see, the height is bigger than this side, and this side here and this angle here are free and cannot move. Let's see what happens. This is the same triangle. Notice there's BD. There should be a ray or side here. Watch what happens when I try to bring this 3 down to make a triangle. Notice that the height is 3.06 and the side isn't going to reach. You can see that C is less than D, slightly less, 3 and 3.06. It's not going to make a triangle. So what is the condition which creates, or what's the situation that creates here? Well, as you can see, when this side is less than the height, there's going to be 0 triangles. So that's the first case. Now let's demonstrate or show you the situations or the conditions where you get 1 triangle. In the second situation, you can see I just changed the sides 3 and 4. This totally changes the situation because the height is now changed. And the height now becomes, let me move that in there, the height now becomes 3 times the sine of 50. Now notice that's about 2.29, and this side, which we can move, because this angle is not fixed up here, is now bigger than 2.29. Let's observe what that looks like in this script. I tried to get as close as I could to having 3 of 50 degrees and then 4. Watch what happens when I move this side down. You can see now, I didn't intend to change the angle, but you can see I'm trying to get close to 50 and 3. As I move this side down, you see there's the triangle that's formed. Notice that it's bigger than the height, but it's also going to sweep past here. So the only triangle that exists is this triangle. And once you know there's one triangle, you can easily use the law of sines like you've been doing to solve this situation. Now let's take a look and see what happens when we have a two triangle situation, or the conditions that create two triangles. Before I move on to the two triangle situation, let's summarize what we learned about one triangle. What creates one triangle is when, well, there's two situations that can occur. If this side is equal to the height, then you have a right triangle, and there's therefore one triangle. But what we just learned is that this side is bigger than both the height and this third side. It also could be equal to this third side. You're going to have one triangle. So that's the summary there. Now let's move on to two triangles. I'm now going to make this third side a measurement that would create two triangles. So first, let's wrap up what we did before. If this side, the height still is 2.29. If this side is bigger than the height and the third side, like in the previous problem was 4, if we make it 5, if we make it 6, that's going to create one triangle. And if we make it anything less than 2.29, it's going to be no triangles. Like this side's 1, or that is, this side is actually 2. There will be no triangles. Let's put in a number that's in between the height and the third side, and let's demonstrate why that would create two triangle situations. So here we have 2.5. It's certainly bigger than the height, so the triangle exists. What makes it create two triangles? What happens there? Let's go back to the script, and you can play around with this on the web page if you'd like. Here's the situation as best as I could describe to get it. This is a 49.9 degrees instead of 50, and that's 2.98. But here's the 2.5 side. Let's swing it down and see where the two triangles come from. First, the triangle that most of you will get with the law of sines is this one. But notice that I can bring it past the height, and since it's less than the third side, you can see there is the second triangle right here. So there is two triangles that are created with this situation. And to summarize it, if this side here that's moving, in this case 2.5, is bigger than the height and less than the third side, it's going to be able to swing around and create two triangles. It looks like here's an obtuse triangle with a 50, 2, 3, and 2.5. And then over here, an acute triangle with 50, 3, and 2.5.
So for the diagram on this one, you're going to want to draw the two different triangles. Draw the triangle that was acute, this one you see on the screen now, and then draw the other one that was just shown, the obtuse triangle, for the second triangle in that space.
Well, let's summarize this, what creates two triangles in a summary. You get two triangles when this side that could be moving, because this angle is locked, is bigger than the height and then less than that third side. In the second clip, what I'll do is demonstrate how you get those two triangles. Everybody's going to be able to get the one triangle using the law of sines when one triangle situation exists. And now you'll know by the test, if you test for 0 triangles, you won't have to do anything. Just calculate the height and compare that to this side here. So in the second clip, I'll demonstrate the two triangle situation and how you find those two triangles.
Okay, so take a moment to review what you have for your triangles, diagrams, and your summary on this chart here. And you can pause the video and read through it and make sure that it matches what you have. And then this next piece here just kind of summarizes it in another way. So you can take a moment to fill in these missing blanks and pause the video and then check your answers. All right, so here are the blanks for the acute triangle in which we just observed. Okay, go away. All right, now we're gonna take a look at the obtuse case. So I'm just gonna draw a few diagrams and just kind of walk us through the obtuse case. So now when the given angle is obtuse, so in all the examples that we just saw, the given angle was acute and it was 50 degrees. But if the given angle is obtuse, we only have two situations. There's not an option for two triangles. There's only an option for 0 triangles or one triangle. Okay, so it's going to be the kind of the same situation. Either the side given the opposite angle, or the side opposite the given angle is going to be long enough, or it's not going to be long enough. Okay, so let me just sketch an obtuse angle here. So here's an obtuse angle, and I don't know, it doesn't really matter what it is. We'll call it angle B, some obtuse angle. So in order to have the case of SSA or ASS, that means we have to be given the side that's opposite B. So we know this side, little b, and then we'd know another side. And the other side I'm going to draw in right here. We'll call that one side C. So those are the things that are given, okay? So the red length, we don't know how long that red side is, okay? So the zero triangle case is if, I drew that one a little bit too long, is if this side B is not long enough to reach. So if I take this side B here and I were to try and swing it, because this is my pivot angle here at the top, it's not gonna reach. So it's not gonna reach if it's a little bit longer, it's still not gonna reach. If it's equal to side C, it would reach, but would it make a triangle? No. So if the side opposite the angle is less than or equal to the other given side, it's not gonna be long enough to reach. And in the case of equals, it will reach, but it won't make a triangle. It'll just make an angle. So the only way it's gonna make a triangle is if this B side is a little bit longer, and when I swing it now, oh, now it reaches, so it would make this triangle. So that side opposite the angle is greater than the other given side. And then it reaches and it makes a triangle. There's no option here for a two triangle case because the angle that's given is an obtuse angle. And the only way it could reach twice is if it were an acute angle because it would hit in two different places, okay? All right, so let's take a look then at some examples. Number one, solve the triangle. So we're given measure of angle B, and side C. So again, for consistency and for keeping my brain focused, I like to always draw the given angle on the left-hand side and the given side on that left-hand side as well, okay? Keeps it consistent so I know which angle is what I like to call the pivot angle, and then I know which sides and stuff have to stay in place. So we're given angle B is 59 degrees. So I'm gonna put angle B right here on the bottom left-hand side. Side B is 4, so that goes over here, 4. And then side C is 14, that goes right here, 14. So I'm always gonna set it up like this. Maybe that 4 is long enough, so maybe it's long enough and it's gonna hit, maybe it's not long enough, I don't know yet. What do I need to calculate in order to determine if it's long enough? So you should be thinking about calculating the height, so we're gonna go ahead and just calculate the height. So the height here, using our SOHCAHTOA, is going to be, the height is equal to 14 times the sine of 59 degrees. So you calculate your height to be about 12.00, and so then you can see that this side of 4 is not long enough to reach, right? It's actually going to be too short, so if I were to swing it, it's not going to make it to touch the bottom. And if it doesn't make it to touch the bottom, then it's not going to make a triangle. So it would go something like that, not long enough. Therefore, we have 0 triangles. So what you're going to do, you're going to write that out. Therefore, 0 triangles, no solution. Since B is less than H. Or you could write it out in words, the side opposite the given angle is less than the height. All right, example number 2. So you want to go ahead and draw your diagram and get this triangle set up. Okay, so here's your diagram. And so we're going to start off by calculating the height. So calculate the height and see if the side of length 10 is even long enough for it to reach. So we have our height is 7.46. And so when we ask ourselves, is it long enough to make a triangle? So yes, it is long enough to make a triangle. And is it possible for it to make 2 triangles? And the answer to that is also yes. So we have a 2 triangle case here. So this side here can swing, and it's going to swing around and hit again right there and make a second triangle that's going to have a segment go like this. So let me draw that second triangle over on the right so I have some space, because I'm going to now have to calculate 2 triangles. So it's kind of like you have 2 problems in one. So my angle A ends up there, 35 degrees. Then on my second triangle, this is going to be my angle B. This will still be my 13, opposite angle B. And then angle C is at the top, little c is at the bottom. And also my 10 for angle A across from that is there on the diagram. So here we have our second diagram. I'm now going to erase that on the first one, just so we don't get confused. And so we're going to go ahead now and we're going to do law of sines to calculate each of the two triangles. So you can pause the video, and with the first one, just use your straight up law of sines with triangle 1, and just calculate using law of sines to find all the missing sides and angles. So the first thing you find is angle B, and then when you find the angle B, we're going to need to use it again. So put a little arrow and show that you're storing it in your calculator as angle B. So next, find angle C by using triangle sum. So we get 180 minus angle A, the quantity of angle A, plus, and then you can just put capital B there because you stored angle B in your calculator. And then you calculate that, and you get the measure of angle C is equal to 96.79 degrees. And I'm going to put these on my diagram as well, so I know what I have, and I know I'm using the right things in the right places for my future calculations. So my last thing then is to find the measure of, or the length of side C, and so I can just find the length of side C by using my last law of sines. All right, so there we see the calculation for little c, and we get 17.31. So we're done with the first half. Now we have to find the second triangle. Okay, so we're moving over to the second triangle, and in the second triangle, you don't need to write this down, you can just watch this part. I can start off the same way. I have the sine of 35 over 10 is equal to, again, I would find angle B first, sine of B over 13. But wait a second, that's the exact same thing that I have over here. So it's gonna give me the exact same answer. This is where you have to be smarter than your calculator, okay? I want you to think about why the calculator will always give you the same answer and why there is a different option. So think through that and see if you can figure that out. So how are we going to find the correct angle B for this second triangle? So if we think about how this triangle was made, we took our original triangle, which had side B going this direction, which was 10 units. This came out longer. And then this side pivots on that top angle over to meet right here. So if you look and consider then this triangle here that I'm just highlighting in orange, this triangle is an isosceles triangle. In an isosceles triangle, we have our legs congruent. If the legs are congruent, the angles opposite, those base angles are congruent. And so what we saw from the first triangle here, 48.21, is this angle right here, 48.21, which means that this angle is 48.21. Which means that the angle B that I want is not going to be found by using that formula, but the angle B that I want here, I'm going to call it B2, measure of angle B2, is going to be the supplement of B from the first triangle. So I stored the B from the first triangle in my calculator as B, so I can just simply write 180 minus capital B, and then I get that the measure of angle B2 is approximately 131.79 degrees. And now with my B2, I can find the measure of angle C2. So the measure of angle C2 is going to be 180 minus, and let's store this. I'm done with my first B, so I'm going to store this one as capital B again. So 180 minus 35 plus my new B, and I can calculate that. And I end up with that the measure of angle C2 is approximately 13.21 degrees. So then last, I'm just going to use law of sines and this information to find my little c2, and I can store this in my calculator as capital C, and I can calculate my little c2. So go ahead and do that, pause the video, and then check your answer. So you should end up with 3.99 for side C. And be sure that your value is accurate to the exact decimal place that I have. If you don't use stored values, you might be off by a tenth or something like that, and you will lose points. All right, let's go on to example 3. So example 3 now talks about find the area of a triangle, given some information. So if I draw this triangle out, I'm going to see that I have angle B, side A, and side C. So angle B is here, little b would be there. Oh, it's an obtuse triangle, so let's go ahead and draw the obtuse. So angle B, 130 degrees, Put A there. Here, this is 92. And then angle C is there. And so here we have 30. Those are in centimeters. We want to find the area of this triangle. And so to find the area of a triangle, the formula that we know is area equals 1/2 base times height. And we can take that formula of 1/2 base times height and we can develop it into another formula that's going to allow us to find the area of this triangle pretty quickly by applying this new formula that uses a sine. Okay, so let's take a moment to derive the formula that we're going to be using in this problem. And I'm going to do it with an acute triangle, but you would have the same concept for an obtuse triangle. And I want you guys to think about how would you adapt the proof to be for an obtuse triangle as well. All right, so if we start off with a triangle and we're given information about side, angle, side. So I'm just going to put angle B, angle C, angle A again. And so the information that we're given is we're given angle B, we're given side A, and we're given side C. And with this information, we want to develop a formula that we can use to find the area of a triangle whenever we're given side, angle, side. Okay, so please note that this is for when we're given side, angle, side. Well, what we know so far is we know that the area of a triangle is equal to 1/2 base times height. So let me drop in the height here to side C. And so 1/2 base times height tells me that my area is going to be 1/2. The base is side C, so side C, times the height. And now I want to think about how can I write the height? Well, since I know that the height is perpendicular and then it's going to form a right triangle with angle B on the left-hand side, I can find the height using SOHCAHTOA with the triangle on the left-hand side, this green, or not green, this purple triangle. So using that purple triangle, I can find the height. You can write this out, but you don't have to, so I'm just going to do it in the head. So angle B is equal, sine of angle B is equal to H over A, so that means that the height is equal to A times the sine of angle B. And this is the formula that we can use here. And so what we're going to notice, so our area is equal to 1/2, I'm just going to put alphabetical order, AC sine of B. What we notice is this here is the product of the two sides, and the sine is of the included angle. So this is the included angle, and this is a side, this is a side. And so that's why this works for side, angle, side. Now, I said this formula will work no matter what. If we're given angle A, you would just use the right triangle on the right-hand side, and then you would need to be given side B and side C to give this SAS situation. So challenge yourself to draw an obtuse triangle, which we have right here, but how would you prove that this formula actually holds true for an obtuse triangle? All right, so let's go back to our example. And so now we can use this formula. So our formula is area equals 1/2 the two sides that are given, A times C times the sine of the included angle. And again, it has to be an SAS situation. You have to have that included angle. So I just plug in, and so I get 1/2 times 92 times 30 times the sine of 130, and I just simply calculate on my calculator. And the answer that you should have found on your calculator is 1057.14 centimeters squared. It doesn't say what to round to, but we'll just round to the nearest hundredth if it is not given. Now take a moment to read example number 4 and pause the video and see if you can set up the diagram for part A that illustrates the problem. All right, so take a look at your diagram, take a look at my diagram, and see if you agree with the placement of the variables and the 2 miles. So there's our diagram that illustrates the problem. And now we're gonna do part B, which is write an equation giving the distance between the plane and point B in terms of theta and phi. And so that distance is gonna be this orange segment right here. So we're gonna call that D. So I want the value of D in terms of the 2 angles that are given. So this is not a right triangle. We have a non-right triangle. So I want to think about how could I use something that I know, probably law of sines, so that I can represent D. So if you want to take a moment to pause the video and see if you can figure this out by using a law of sines formula and solve for D in terms of only theta and phi. All right, so what you might notice is that you already have one pair that you can use for the law of sines. We know here theta, and we know side D because we need to solve for D in terms of theta. So I'm going to start with that. And so I have to start the sine of theta over D is equal to. Now, what I next notice is that I have another side. The only other side that I have is this 2 miles. So in order to use this 2 miles, I need to find this angle up here in the upper right corner. And so in order to find that angle, I'm going to need to think a little bit about my geometry. And so what I can remember is if I draw a parallel line here from the plane, such that that line is parallel to the ground, then I know that this angle up here is also theta. Because if lines are parallel, alternate interior angles are congruent. Similarly, I know that this angle here, phi, is congruent to this big angle right there. By the same reason, if lines are parallel, then alternate interior angles are congruent. So that is phi, that whole big angle, which means that the angle that I want inside here is going to then be phi. So let me try to squeeze that little arrow in there. That's going to be phi minus theta. And so then I can use that along with the 2 miles, and I can say that the sine of the quantity phi minus theta over 2. And then all I have to do here is solve for side D. So I'm going to go ahead and cross multiply. So I get D sine of phi minus theta is equal to 2 sine of theta. And then I solve to get D. So I get D is equal to 2 sine of theta divided by the sine of the quantity phi minus theta. And now I've written an equation for the distance between the plane and point B in terms of theta and phi. And that's the end of lesson 6.2 part B, or sorry, 6.1 part B.